Okay, so let's talk about some higher derivatives. So since the derivative of a function f of x is another function, f prime of x, what's to stop us at taking the derivative again? That is the derivative of f prime of x. What would that look like? What could it tell us and how can we notate it? So if we were looking at this, the first derivative of a function f of x is denoted by f prime of x, and that's just going to be taking the limit as h approaches 0, we've already learned this, of x plus h minus f of x all over h. If you looked at the second derivative, that's going to be taking your first derivative function and doing the same thing. Limit as h approaches 0 of f prime of h, because you're taking the derivative of the first derivative. So the second derivative is the derivative of the first derivative. What do you think the third derivative is going to be? That's going to be the derivative of the second derivative. So that's going to be the limit as h approaches 0 of the second derivative. So we'll get that. Okay, let's look at an example. A ball is launched vertically into the air from the ground with an initial velocity of 96 feet per second. Its height s of t is 96t minus 16t squared. Find and interpret the first and second derivative, then interpret the results in context with units. So if we're looking at this, we can see here's our height function. We can assume this is in terms of feet and our time is in terms of seconds. So if I find that first derivative, in the context of this problem, and we've done this one before, this is going to equal the velocity. So always the derivative of the position function is the velocity function. So when I find that derivative, that's going to be taking the limit as h approaches 0 of s of t plus h minus s of t all over h. And we did this one previously, and when we did, we found that it was 96 minus 32 feet per second. So this just means that the velocity of that ball is 96 minus 32 feet per second. So that's the velocity function. Now, if we're finding the second derivative of the position function, that actually stands for the acceleration. So the second derivative of the position function is going to be taking the derivative of the velocity. So that's going to be taking the limit as h approaches 0 of 96 times t minus h. Oops. I was doing the wrong function again. All right, so going to that velocity, which is here. So 96 minus 32 times t minus h minus the quantity 96 minus 32t all over h. When you go through and simplify this, you're going to be left with the limit as h approaches 0 of negative 32h over h, which just gives us a value of negative 32. In terms of units, we had velocity in the numerator, and that was in terms of feet per second. And again, we've got our time. We're taking this with respect to time, so that's per second. So that gives us negative 32 feet per second, which is like second squared, is another way that we can write this. So this means the acceleration function for this ball is negative 32 feet per second squared, which makes sense in the context that gravity is negative 32 feet per second squared.